So in this video, I want to have a look at high-speed propellers. So let's begin by looking at an aircraft that has a rectangular platform. Let's assume it's an Airbus A350. So as the air flows over the wings, what we don't want is the airflow to get above Mach 1, because there are drag effects and movement of the CAG and so on. So, we try to limit the airflow over the top of the top surface of the wing. So if the aircraft is traveling forward at Mach 0.8, we need to reduce this value here as the airflow over the wing speeds up. We just need to make sure that this is below Mach 0.1. Sorry, Mach 1. So how is that achieved? Well, on this aircraft and essentially all aircraft, it is achieved by using Wing Sweepback. So if I take a look at a Wing Sweepback, it has that sort of shape, and let's look at that a little bit more closely. So here is our sweepback shape. The angle of sweepback phi is the angle between the leading edge and the lateral axis. So for the A350, for example, it is approximately 32 degrees. Now I'm just going to complete my triangle here, and we're going to include the airflow coming over the wing. However, what really interests us is the airflow that is normal to the wing. So the airflow that's perpendicular to the wing, because that is the airflow that generates our lift. And I'm just going to expand out these sides of my triangle. Okay, so I've expanded out the sides, and now I want to look at the airflow that's normal to the wing. So the airflow here is coming in, it's at right angles. It's at right angles to the leading edge. So we have a triangle here and here, and let's bring the normal velocity forward. So there's our normal wing velocity. So I have 90 degrees here, I have 90 degrees here. This angle must be equal and opposite to this angle. So if that's 90 degrees and that's 90 degrees, and if that angle is equal to this angle, then this angle here must be equal to phi. So now if I want to look at what effect that has on the airflow over the wing, or the airflow that's normal to the leading edge of the wing. Let's assume we have a velocity VA of 100 meters per second. We have a sweepback angle of 32. Well, then the airflow that's normal to the wing is 84 meters per second. So, if I had a wing that had a rectangular platform, and it was, if this was 100 meters per second, then the airflow that's normal to the wing is 100 meters per second. If we have an airflow here and it's 100 meters per second, the actual airflow that goes over the wing, normal to the wing, turns out to be 84. So, this allows us to fly the aircraft a little bit faster. So if I fly this, we want to avoid the speed of sound. Let's say it's 340. So if I get to 340 meters per second, so 340 in this direction will be about 288 meters per second. So we have a little bit of leeway. We haven't reached Mach 1, so we can cause the aircraft to fly that a little bit faster. In fact, let's work it out. So if we're saying we want to keep this velocity here below the speed of sound, 340, and then what is the speed of the aircraft? Well, then it's VA times cosine 32 is going to be the 340. That means VA is 340 divided by the cosine 32, and that is 400 meters per second. So if we had a rectangular planform, we'd be limited to flying at just below 340 meters per second. If we have a sweepback, we can now increase our velocity to just below 400 meters per second. So there is some benefit to it. So how does that apply to a propeller? Well, with a propeller, we have this type of sweepback shape, and that allows us to rotate the propeller faster. So we'll look at that in a different video.